Students, once again I welcome you all in my channel Physics Classes. You are requested to like and subscribe my channel so that you may receive videos whenever I produce on various topics. Today I have started the new unit electromagnetic induction, and the first video in this unit is on the topic magnetic flux. Always I say to you that every physical quantity has two different definitions. One is called qualitative definition and one is quantitative definition. Qualitative definition explains the physical quantity theoretically, and quantitative definition gives its numerical values or numerical operations. So first of all, theoretically magnetic flux passing through a surface is defined as number of magnetic field lines passing through the surface. Number of magnetic field lines. Students, remember, number of magnetic field lines passing through the surface is called magnetic flux. Now, how will you define it numerically? To define magnetic flux numerically, we suppose this is a surface. This is normal to the surface. I have represented by n cap, and electric field is inclined at an angle theta. This is a magnetic field. Magnetic field is inclined at an angle theta with the direction of area vector. Then the component of magnetic field towards area vector will be B cos theta. Normal to surface, B cos theta. So magnetic flux is defined as the product of magnetic field normal to the surface and area. B cos theta is the component of magnetic field normal to the surface. In this diagram, you can see the component of B in this direction will be what? B cos theta. So B cos theta multiplied with area becomes magnetic flux. You can say phi is equal to BA cos theta, or you can write phi is equal to B vector dot A vector. In the given diagram, n cap is the direction of area vector. So remember, magnetic flux passing through a surface or linked to a surface is given by the dot product of magnetic field with area of the surface. Dear students, magnetic flux is a scalar quantity because it is the dot product of magnetic field and area. Now the question is that magnetic field may not be uniform in every case. It is not necessary that magnetic field is uniform. In case magnetic field is not uniform, we consider a small area dA over which the magnetic field may be considered uniform. We consider what? A small area. A small area dA over which the magnetic field is uniform. So magnetic flux passing through this area will be given by d phi is equal to B cos theta into d. Again, what is theta? Same. Angle between magnetic field and area vector. Therefore, d phi is equal to, students, B vector dot dA vector. So in this way, we have calculated the magnetic flux passing through a small area. In order to calculate magnetic flux over the whole surface, what we shall do? We know when small is given, total is to be calculated, we have two functions, either summation or integration. When the physical quantity is discrete, for example, mass of the students is given and you have to calculate the total mass, what we shall do? We shall do summation. But if a physical quantity is continuous, then we use integration. Since magnetic field is non-uniform but continuous, that's why we shall do the integration. And magnetic flux is then given by phi is equal to integral d phi, that is integral b vector dot a vector. So remember that in case of non-uniform magnetic field, first we shall calculate the magnetic flux over a small area, considering the magnetic field to be constant, and then we shall elaborate it and integrate it to calculate the magnetic flux over the whole surface. Now there are certain special cases. Number one, suppose the surface is placed normal to magnetic field. Surface is normal to magnetic field. So when surface is placed normal to magnetic field, then area vector and magnetic field both are parallel. As such, theta is equal to 0. And when theta is equal to 0, phi is equal to b cos theta. Theta is equal to 0, cos 0 is 1, so flux is given by simply what? B. It is the maximum value of magnetic flux passing through the surface. So magnetic flux passes through the surface when the surface is placed normal to magnetic. Second case, suppose this is a magnetic field and surface is placed parallel to magnetic field. If the surface is placed parallel to magnetic field, then normal to the surface makes an angle 90 degree with the direction of magnetic field. Suppose this is the magnetic field, this is the surface, surface is placed normal to magnetic field, so angle between them is what? 90. Angle between normal to the surface and magnetic field is 90. So flux phi is equal to BA cos theta, theta is 90, so it will become 0. So when the coil is placed parallel to magnetic field, the flux passing through the coil is 0. And if, third case, if normal to the surface and magnetic field are oppositely directed, this is magnetic field, this is normal to magnetic field, they are opposite to each other, then theta is equal to 180. Cos 180 is equal to minus 1, so flux is equal to what? Minus BA. In this case, magnetic flux is negative. So keep in mind, very important point, surface is parallel perpendicular to magnetic field, then magnetic field and normal to the surface are parallel, flux is BA. In this case, normal to magnetic field and surface are normal to each other, that is theta is equal to 90, flux is 0, and if the coil is rotated by 180 degree, then flux is minus B. Students, magnetic flux, already I have told you is a scalar quantity. SI unit of magnetic flux is Weber. Serious unit is Maxwell. 1 Weber is equal to 10 to the power 8 Maxwell. That is the relation between Weber and Maxwell. And what is the dimension? Dimension of magnetic flux is m L square T power minus 2 A power minus 1. Suppose you have to define 1 Weber. What is 1 Weber? So when a coil of area 1 meter square is placed normal to magnetic field of 1 Tesla, then magnetic flux passing through it is 1 Weber. What is 1 Weber? A coil or surface of area 1 meter square is placed normal to magnetic field of 1 Tesla, then the magnetic flux passing through it is 1 Weber.